Up to now, the vast majority of the data that we've been operating on with neural networks has been image data. Starting this week, I'd like to broaden that a bit and think about ways that we can use neural networks for other types of problems. And we'll start by thinking about how we can give text data as input to neural networks. With image data, standard digital storage formats with arrays of red, green, and blue pixels are quite convenient as inputs to a neural network. This works so well because the arrays capture spatial relationships between the pixels, and because the pixel values capture color intensities that are directly relevant to the sorts of computer vision or image processing tasks that we're trying to solve. For text data, on the other hand, the way to represent a document as input to a neural network is much less obvious. The standard digital representation of text, where we convert characters to ASCII or other digital values, is much less directly relevant to how neural networks learn. We could imagine various ways of converting these ASCII values into something that would be at least valid input to a neural network, like taking the binary representation of the ASCII values, or normalizing the range of characters in the alphabet that we're working with to lie between 0 and 1, and then constructing vectors of those character values for each word. But neither of these representations is meaningful in anything close to the same way that the array representation of an image is. If we think about words that are similar under these representations, in the normalized vector version, cat and car are identical in all but one dimension, where they differ by 0.04. Whereas in the binary vector version, cat and sat differ by a single bit flip. And so a neural network that's trying to make generalizations based on these numerical values is going to be fooled an awful lot by getting very similar numerical values that have very different semantic meanings. One alternative that might seem a little crazy at first would be to create giant vectors which are one-hot encodings of our entire vocabulary. So we have a vector with an enormous number of dimensions that is mostly zeros, representing all of the other words in our dictionary, and then a 1 in the position of the specific word that we are trying to represent. The size of this vector is the number of words that we would ever expect to encounter, so think on the order of 1,000,000 dimensions. This does solve the problem of words that are semantically very different being represented very similarly, in that every word is represented completely differently by being literally the only word to have a 1 in its particular dimension. If we gave documents where each word was represented this way as input to a neural network, then the network would be forced to learn different weights for each word because each word is a totally separate input neuron. But the problems here should be obvious, that we've swung much too far in the other direction towards having words be dissimilar and towards having a gigantic expansion of the number of dimensions required to represent our data. So it's worth enumerating what we'd like our representation of text data to actually achieve. So it makes sense to have a per word representation, at least if we are representing English, and we want it to be the case that our vector representation of each word is not too gigantic in terms of the number of dimensions, for reasons both of data storage and learnability. And we'd also love for this numerical representation to carry some amount of actual semantics. That is, words with similar meaning have similar vector representations, and words with completely different meanings are not represented by similar vectors. Finding a good numerical representation of text documents to do machine learning on has been a big problem in natural language processing for a long time. But in the last 5 years, there has been great advancement in this area by using neural networks to solve the problem of generating an appropriate input representation to our neural networks. A key prerequisite to this sort of training is extracting n-grams from text data. An n-gram is just a sequence of n words, so a 5-gram would be a sequence of 5 words that we extracted from a text document. So, from this example sentence, if we were to extract all of the 5 grams, the first 5-gram would be the blind application of machine. The second 5-gram would be blind application of machine learning. The third would be application of machine learning runs, and so on. N-grams are useful because they can be mechanically extracted from text documents without any prior machine understanding of what the text actually means. And then we can use those n-grams as a source of context in terms of the surrounding words for any particular point in a sentence or document. And the key idea for generating the representation that we will use for text documents is that we can train using this one-hot dictionary representation as the input to the training, and then pass that to a neural network, which is trying to predict the one-hot encoding of the surrounding n-gram. So for example, we could make the output be the other 4 words in the n-gram represented by their one-hot dictionary vectors, all concatenated together. So for example, one of the inputs in our dataset could be the 5-gram runs the risk of amplifying, and we'd train on the input risk and try to predict the output vector runs the of amplifying. And so by training the network to recognize nearby words using these n-grams, we're not expecting that the network will ever be able to perfectly solve this task. Obviously, for the input risk, there are lots of other 5-grams that it could be a part of. But this should have the effect that semantically similar words should appear in similar n-grams and should receive similar gradient feedback in our neural network training. And to the extent that a network can learn anything on this task, we would expect that it would tend to produce, for any given input, some of the more common contexts in which that word can appear. And in order to do that, it must be the case that by the time we get to the last of the hidden layers in this network, the activations in that hidden layer on a given input word must be somehow a representation of that word and its common contexts that has actively proven itself useful for predicting words that are in actual practice appearing near the input word. And so, to return to one of our favorite tricks, we can throw away the output layer and use the vector of activations at this last hidden layer on the particular input as a numerical encoding of that input. And the result is what is known as a word embedding. Once we've thrown away the output layer, this neural network takes as inputs words in our dictionary and produces as output a vector representation of that word that we know was at least somewhat useful in terms of predicting its context in actual text. There are many variations on the general idea I've shown here for producing word embeddings. What I have presented is a rough sketch of the approach behind Word2Vec, which was one of the first successful embeddings produced by a neural network. But there are a number of newer and more popular approaches based on the same general idea. What we will do in practice is not to train our own word embeddings, but in the spirit of transfer learning, to use embeddings that have been trained by others with more data and more computation to hand. Because once such a model has been trained, it's quite easy to generate a lookup table that lets you translate an arbitrary text document into the word embedding. And so our approach to doing machine learning on text data will be to first pass our document through an existing embedding, and then use the vectorized representation produced by the embedding as the input to our neural network.